Yes? No? Okay. A bit too much. So, the idea here of this present seminar is just to give a short introduction of what I'm doing and why I do care about something which some of the mathematician and physics students are learning. And I just picked a few topics I was working lately, in the last few years, where derivatives actually appear, and some of the derivatives appear in a nice way, and some not so nice, and I'll just try to bring you through. And at the end, you might know more what I'm working on and why a physics professor has to deal with mathematics besides his experimental things. So when we teach physics in the first year, Physics 111, and some of you have been there, we do the following. We show the following graph. This is nothing that you should be scared of, because we will go into deep detail of this. We speak about the trajectory. That is something a particle does when we make a recording of the position of a particle as a function of time. And then we plot it in a coordinate system, which is x and y. And then we look what is the position of these, or the movement of this particle. And here you see here, this is a recording of this movement of this particle as the time progresses, and that is called the path of the particle. Now, this is nice, but we will find out that a lot of the people which are sitting in the back can come to the front, because otherwise you're so lonely there in the back. A lot of times when we do this recording, we're actually not really interested on the trajectory, but we are probably interested into some other quantities. So be it the velocity, the speed of the particle, or as a physics person, we are interested in the acceleration. Why? Because we have found out that all the physical systems are identical if we have a constant velocity between them. That means if we are moving in an inertial frame of reference, all the equations of motions are the same. So it doesn't really matter on the velocity, but it matters on the acceleration. Okay, now, but first we need to get the velocity. And that is what we do, is we take one time, which we call Ti, and another time is Tf. And then what we do is the following. Do we have a laser pointer? If you have a laser pointer, it would be great. Not sure, is there? No. Okay. If there's no laser pointer, then what you see here, we do the following. We speak about an instantaneous velocity, which is defined as we do a limit. And we do the limit the following way. We say that the time delta t, at which we look at the particle, that is the distance between Tf and Ti, we make that very, very small. And we look for the limit of this ratio, delta r divided delta t, and we give it a name. We call it dr dt. And the right-hand side is identical. The left-hand side is a definition. And we do this delta t, we go really to very, very small values. That is, we have to do the mathematical limit process. And when we do that, the particle will move lesser and lesser distance, but then the ratio between delta r and delta t gets to a finite value, and that is called the velocity. Now, sometimes you see that we use not just a normal character, but we use it in bold, and in bold is a vector quantity. So you can define that not only for maybe for x position and y position, but you can define it for a vector quantity, and this can be 2, 3, or whatever dimensions you might come, or it can be imaginary vector in a complex plane. So we call this velocity. Vector v is a limit of delta r divided delta t, and this is called dr dt in mathematics. Dr dt is the ratio between the two. Now, what is this dr and this dt? And that is, if you can just do the following mass. You look at the position of the particle at the time t plus h, and then you subtract it from the position at the time t, and then you divide it by h. You do the limit. This is dr dt. Okay, this is the standard definition of it, and you can, if you know how to deal with this, you will get a derivative of r with respect to t. But if you're doing physics, and especially if you do physics with measurements, you can't do this. Also, you do not do that in mathematics. We can't do it. Physics people are handicapped in that sense, at least if you do a measurement. And actually, we know why we can't do it. Because, or why do you think why we can't do it? Why can't we do this dr dt? That is a limited resolution of our measurement equipment. And the ultimate limit is the atom, and even closer to that is Heisenberg's uncertainty principle. So we are limited. We can't do both. dr and dt going to 0. We can't get it. Or not dr to 0, but dt to 0. So we have actually problems with this limit, and therefore, also in mathematics you can do this limit. We come up with a solution to that. We say, also we can't do the limit. We can do better, and that is what costs all money in research is this delta t. Most of the money actually goes into this delta t, because to be precise with this ratio, you have to make delta t small. Yeah, this is multi-billion. Maybe it's the most expensive equation. I show you some examples why it is expensive. But so be reminded also we can't do it. We try our best. So we need to, for this one we need a time resolution. For the other one we need a spatial resolution, and both of them have to be good enough. So now I show you what you can do if you have good equipment and have sufficient money, and look at the. This should be, I try it once more. So there's a bullet coming from the left to the right. Now you see that, like, York, Nanyang. And another thing, what you see is actually physics. So there's an impact of an object, there's forces acting on it, and then something happens. I'm sorry for the lousy picture, movie quality. So this is not actually what physicists like. They like to do it, sure, but you're not getting paid for that, shooting bullets through something like this. But what actually I'm working on is fluid mechanics, and there is a fluid mechanic problem, which means what you have, maybe the egg, you shoot through it, and then you see the splattering of the egg. There's extremely complex fluid mechanics. There's compressible flow going on, there's spraying going on, surface tensions going on. It's an extremely complicated process. But to understand what actually goes on, we need to measure velocities, for example. How do we do that? So, sorry. That is how we do that is the following. We take a picture with the egg and the bullet. And you see already the problem if you have not too good equipment or don't care too much about quality, you see the bullet not really in focus. Why is that? It's so fast. The bullet is fast, but because it moves during the exposure time, so you don't get it in focus. But the egg is not as fast moving. And later on, you see the bullet at a different position. The egg hasn't moved so far. So the egg is stationary. The bullet is not. So how do we measure our drdt here? Yes, we take a frame. This is frame number 5. And then we look for the position of the bullet after some later frame, call it frame 7. And then, yeah, what else do you need? You need the difference in time. And then, so delta t is our 2 frames, and delta r, yeah, is about 1.5 egg diameters. So we have 2 frames over egg diameters, and then we put it in. Let's see, I hope this movie looks better. So now you see, so these are the individual frames from this movie we just saw. And you see it stepwise moving. So our delta t is rather coarse here. Actually, bullet moves rather quite a distance. I'll show you better movies later. So what is the velocity of it? It's about 1.5 divided 2 egg diameters per frames. Okay. We don't really care, but sometimes people want to know what is your egg diameter, what are the frames. So you have also a standard unit, SI unit, we call it. This would be then, velocity would be egg diameter, wouldn't be that qualifying because there are big eggs and small eggs. But so the standard egg diameter would be meters, and the frames would be the frame rate of the camera. I think it's about 1,000 frames per second, so it's a millisecond. So 2 milliseconds, 1.5 egg diameter is about maybe something like 5 centimeters. So 5 centimeters per millisecond, that would be 50 meters per second. So 50 meters per second is also maybe not something you would know. You are maybe more related to kilometers per hour. How much is it? Yes, it's okay. So 160 kilometers or 70 kilometers. So something in this range, 180 kilometers per hour, is this bullet. This is a nice velocity, but it's not the fastest of the bullets. So it's a slow bullet. It's a cheap camera. I'll show you faster cameras. Okay, but so let's say, and if this impact happens, then you get a certain type of fluid mechanics. If the impact is much, much slower, you will have completely different impact dynamics. So some of people is. So now I show you extremely boring process, what we have done in our lab. That is, we let a bubble rise towards an interface. So the bubble rises up and then hits an interface, and then at one event, eventually it will reach the surface of the glass. No, it doesn't. You think it might, but it never does it, because there's always a little thin liquid film between the bubble and the interface with the liquid. And this film is squeezed very, very longly. And it takes so long to squeeze it, actually the bubble is bouncing away while leaving this liquid film there. So you don't actually thin.
Does the velocity you calculate, is it the velocity at a particular instant?
Oh, very good. So while this bullet moves, it decelerates due to friction, due to drag in the air. So that is at one point, and you can only know the velocity at that part of the trajectory. At later trajectory, it will be lower or higher, depending on.
The average velocity
That is, that what we speak about is the average velocity at that position, r. Yeah? At that position in space, r. That is the average velocity. But this will change, and you would like to come to the limit, delta r, delta t, where delta t goes to 0, which you can't do just by practical purposes, and therefore you will not get the real velocity. That is why we are so expensive in physics. We don't never get the real thing. But you can write down an equation, and you can really do the limit. Whenever you have the functional form, you can do that. Now, this is this boring experiment. You let the bubble rise, let it bounce against this interface, and then you look, and then you look at it. So, why we are interested is actually we are interested in the thin liquid film. How thin this liquid film gets, and can we understand the fluid mechanics inside this liquid film? And you already see here that it's not so trivial, because we use a laser. We use a HS camera as a high-speed camera, and we use not only one, we use two high-speed cameras, and we need some illumination of this one. So that is what we are looking at. We need two pictures. This lower picture is the bubble. When it reaches, the upper part is the mirror of it. And then in between you have a thin liquid film, and this thin liquid film is measured by interferometry. This is something you learn in optics in the second part, I think, of the first semester. In the second semester in physics. But it's just a wave interference, so you look for, you use the light as a ruler, and whenever it's bright or if it's dark, you have a certain percentage of the wavelengths of the light. So here, between bright and dark, is about a quarter of 530 nanometers, so it's about 150 nanometers thickness. So if you see a bright ring and a dark ring, bright ring, dark ring, you have about 150 nanometers height difference. And with this information, you can actually reconstruct the surface. No, just count the rings, the fringes, what they're called. Okay, but I'm not so going too much into detail of this one. Now we have our boring bubble, which rises. And you see the size of the bubble is about 0.5 millimeter. This is much smoother recorded. It's recorded with about 50,000 frames per second. And, okay, and then it sits there. But have you seen it bouncing? Have you seen it bouncing? Really? Some of you might not, but we can actually, what we can do is, we can extract from the movie, we can extract the bubble, and then we can very precisely, to a micrometer position, we know the position of the bubble, and then you look at the position of this bubble. This is now the green curve as a function of time. And then you see the time scale is now about millisecond range, 10 milliseconds, that's where the bubble rises. And then you see it's the position goes up, and then it goes down, and it goes up, and then down, and then it stabilizes on a certain spot. So what we know at the end, the velocity will be 0. Yeah? The rise velocity, it's actually balanced. And before, we have more or less a straight slope. It will be a constant velocity. So initial constant velocity and final velocity. But in between, we have the interesting physics because the bubble approaches, goes back and forth. And there we see actually the velocity. This is the blue line. Initially, it's constant, then it decreases. And then you see it gets actually below 0, and then it increases again. That's when it comes back towards the interface, and then it bounces, and then you see this one. And you see how smooth we can do measurements in physics. It's not the most difficult problem, and if you have sufficient framing resolution, you can make really like, it looks like a graph. And I'll show you in a short while. Sometimes things look different than they are. But it looks really like a smooth graph, and if you zoom in, there will be no more physics. Yeah? There's no small oscillations in this dynamics. Okay, now that can you do, and then now we can actually see the whole movie. The bubble is now oscillating. Yeah? You see it on the bottom, you see the velocity of the bubble as a function while this actually happens. And on the top, you see the interference pattern. That is the representation of this thin liquid film, and it forms only when the bubble gets very close to it. So this is the film, and then you see while the film approaches, you get more and more fringes. And here is the reconstruction of this interface. Okay. So this is and you see actually the scales here. This is about 100 micrometer, whereas this is only a few micrometers. It's a very, very thin film. And now, what you see, actually, there is a small dimple formed. So actually, the interface is thicker in the center of the impact as outside. This is called the dimple. That's where we are after. And this is, you see, 2012, published in PRL. This is current science. This is fluid dynamics, which is of current interest. And we can really realize that. And there are straight lines here. This is the interface profile. There's straight lines through it. That is the beauty. We can just use our fluid dynamics equations and model this whole experiment and see if the model is sufficient to explain that. And indeed, it is. So it was a very nice experiment and modeling, because using the model, we can show it is correct up to our measurement resolution. And now I show you the model. I don't want to scare you, but this are the type of models we are dealing with. This is a fluid mechanic model. dH dt, that is the velocity of the interface. Yeah? Not dr dt. H is the thickness of the interface. And then there are a lot of other numbers inside. R is this position, the radial position. And then there are some other things. Pressure goes in and stuff like this. And then these equations, they can look much more nasty. And you need a mathematician to solve it. I can't do it. There are people who can solve this analytically. Indeed. And actually, indeed, there's one of the authors is a mathematician. Okay. So these physical laws, this was just one for fluid mechanics, they are based, many of them are based on Newton's second law. Let's just write it for fluid. And when you look at the Newton's second law, actually the first equation is Newton's first law. The sum over the forces, when the sum over the forces is 0, the velocity doesn't change. The velocity of your object doesn't change. So it will remain in a constant motion without change in velocity if there is no force acting on it. That's the first Newton's law. And the second Newton's law is if there is an acceleration, only if there is an acceleration, in an inertial frame of reference, then a force is acting. So if ma is not 0, then the force is acting. Or actually, it's a definition of a force rather than a real law. But we call this a force whenever the acceleration changes. Okay, this is one. Do you know this equation, set of equations on the left-hand side? Oh, I've got physicists or mathematicians knows it too. Math people don't know it too? No. Math? You know it? Wonderful. But actually, they're wrong. Who knows which of the 4 equations is wrong? Maxwell didn't know at that time. We know it only since a few years. Oh. Okay. The second one. Second one is wrong. This one actually says there are no magnetic monopoles. The magnetic field is a solenoid. There are no monopoles where if you can have charges which create, this is the first one, charges which create an electric field, there are magnetic charges somehow come always in pairs, and there is actually no net magnetic charge. That is this equation. The second one says it, but people have found magnetic monopoles. So one has to think about how to correct for it. But it's very easy to correct, and the equation become much simpler. Okay, but what you see on this equation here, d dv dt, that we call a full derivative, and the other one is a partial derivative. This partial db dt, this delta d, this is different sign for it. They both are more or less actually the same. This one just specifies you do only derivative with respect to t, not any other. And I'm not going into detail, but we have actually, as a physicist, but also as mathematicians, you have two types of derivatives, or two different ways to make a derivative. I'm not giving a math lecture here. You'll learn that. So this is a rather interesting experiment. We see something moving, and then it is not moving as you would actually expect. And that we see if we take a derivative. Now, what we did here is we created a tiny robot, and we can operate the robot by putting a sound field to this small piece of plastic, which is a robot. And this is done by a loudspeaker. It's a piezo transducer, which is glued on the backside of this glass flask. And then we had a glass tube inside, where we put the robot inside, here. And then we take a camera, and we look just for this robot at that spot. You don't see the robot here, but you see it on the next slide. So this is a zoom-up version of a robot, and it's extremely cheap. So what you take a small Teflon tube. This is transparent. You glue one side with a glue head on one side. Then you fill it with a bubble. This is the black part. The bubble is here. From here to here is a bubble. And everything around is water. That's it. Just put it in there. And now you switch on the sound field. The sound field actually changes the pressure, which changes then the size of the bubble. So the bubble will oscillate, because the sound field is oscillating. So the bubble will oscillate. And interestingly, if it oscillates, the whole thing moves to the right. Yeah? So now on the bottom you see the time scales, 0.6 seconds. And now if we zoom up, we just look at this interface, you see that this moves back and forth, yeah, like periodically, and the whole thing moves out. So, okay, this is cute little thing. But what would you say, what is the velocity of this object? I can play it once more. Now, the velocity of this object. You can do image processing and extract the position of it. It looks like a linear velocity, huh? Maybe more or less like constant velocity. It is, if you don't use a high-speed camera. But if you take a high-speed camera, you see it's not. And that's why we can't just, it depends really on the temporal scale where we do our derivative. So that is actually the velocity. And this is not a function, but this is measured. So the position of this end of the backside of this thing, which moves to the right. And it moves up and down. So it does actually 2 steps forward, and then it does a step backwards, and 2 steps forward. So it's an oscillatory movement. And now, when I write here v, 1.3 millimeter per second, that means that is the average velocity. It looks very much linear, but on top there's an oscillation on it. So how do we get this velocity? The real velocity of it. What we do is we just take the position, call it x, is the velocity times time. And then we have on top, we have an additional oscillatory velocity. So now I ask you, what is the velocity? Who's first year math? First year? Okay. So tell me, what is the velocity of this object? Or you can pass over to a colleague. So how do you do it? How do you calculate the velocity of this object? I don't want to hear a number, I want to see the formula. This is the position. So minus a sine. Minus a is omega sine of omega t. Yeah? So you have two parts. You have v0 and you have a minus a omega. So you have a v0 and a omega. And sine can only change between between minus 1 and 1. So you compare these two. Depending on omega and a, you might have a very, very high velocity. Also, the whole thing moves with 1.5 millimeters per second. Now, if you put in the numbers, that you see on the graph. Yeah? So this is the velocity. Sorry. This is the instantaneous velocity here. And it goes up to 6 centimeters per second, whereas the whole thing moves with 1.3 millimeters per second. So the instantaneous velocity can be much, much larger than the average velocity. And the average velocity, here you wouldn't see it on this graph. Yeah? Over 1 second, if you don't have a sufficient resolution, you wouldn't see that this one is actually jiggering back and forth. So again, remind you, if you want to do good physics, you want to find something interesting, you need to pay money for this delta t. That's the way to do it. You wouldn't see it if you wouldn't be able to resolve that time scale. And I know people working with atoms, they need other equipment, but it's much more expensive than what I'm doing. Now, the velocity of this object is interesting, but it's actually more interesting what is the velocity of the fluid. And that is a bit more tricky to look at. You can't just take the picture of a fluid particle because it's transparent. So what you do is you put particles into the fluid and assume the particle is following the fluid motion locally. And this is an experiment where we look for the fluid particle, and we see actually that in the central line, there's fluid motion moving out, and from the sides, fluid is rushing in. Depending on actually the oscillation cycle, you get these rather complex flow patterns there. And they explain why this whole thing moves to the right. It's like a jet engine. It's pushing liquid out, and this leads to a momentum transfer onto this object. So that is...
It's supposed to be in 3 dimensions.
Yes. They're all three-dimensional, so what you use is a camera which makes either you make a light sheet, I come to the next slide, or you make the recording such that you have a very narrow depth of field. So you have record the particles in focus in a very narrow range. So, but for sure you always have a 3D effect, so particles might leave. So this is a picture. So you have how you do it. You put particles in your flow, and then you take two pictures of the flow at 2 different times, T1, T initial, and T final. And then you look for the displacement of the particle as a function of time. So you get the particles in this picture, you get the particles in this picture, and then you look how much the particles in this picture have moved from the particles in the other. And if you make that area very small, you get a very high resolution of your particle field. There is a technique called correlation. It's called cross-correlation. So you make actually a correlation of the 2 pictures, and then you find the position, the most probable displacement of the particles. And from this you can find the displacement of the particles. And then you know the time between the 2 pictures. You know delta t. You get the velocity. And this way you can measure the velocity in the fluid using particles. It's called particle image velocimetry. And then if you do that at many, many spots, you get a rather detailed one. Now, I did some research in the Netherlands, and in the Netherlands, you know about windmills. So whenever they see an engine which works on bubbles, they would do a windmill also as built on bubbles. And this is, I think. So, and I have the sound on here too. So this is each of these small tubes, there's a bubble inside, and it oscillates, and each pushes. And therefore, if you have all these together, you make actually a motor out of it. And the sound you hear is the resonance frequency of this bubble. It's about 1.5 kilohertz. So it's a very nasty experiment. You don't like to run it for a long time. Okay, so I'm not sure. I have a bit more time. So I have, I showed you these nice bubbles. These bubbles were rather kind to us, but there are also bubbles which are a bit destructive. And here, this is a kidney stone, a phantom of a kidney stone. I just run it a few times. And you can actually create these bubbles near to the phantom by some acoustic means. I don't go into detail. And they can be destructive. They can destroy the kidney stone. And that is a very nice technique to destroy kidney stones without opening the body. You can do that by some external sources. But there are bubbles generated, and these bubbles are oscillating, and you can do a physical model of the dynamics of these models, of this oscillation of these bubbles. And what you need in is actually the bubble radius. You have some bubble content, you have a surface of the bubble which has some interfacial tension, you have pressure, you have velocity, and all these things. This is the physics business. So a physicist will come up and say, oh, this is interesting, this is interesting, this is interesting. Okay, we built all the model out of it. So you do that this way. This you will learn in your lectures and maybe in your research attachments. Lord Rayleigh, he was the first one. He had said, okay, let's put all these things together. And then another clever guy, Placid, okay, I'm better, I know more. So they put things together, and they come up with an equation of the bubble as a function of the pressure. So if you change the pressure around the bubble, it will oscillate, as we have seen already. And if you do that a bit more nasty, the whole thing looks a bit different. It's not just a harmonic oscillation, but you have indeed an ordinary differential equation. I'm not sure if you will cover this in this first semester, but this is something you should care about too, ordinary differential equation, because in physics, most of our equations are given in this way. Sometimes they're given as partial differential equations, then they are even more nasty. But why is this one already nasty enough? Because it's not a linear ordinary differential equation, it's a nonlinear ordinary differential equation, and I can assure you there's nobody who can solve this guy. You can't integrate this guy anymore. It's too nonlinear. And it has all aspects of what you can imagine what is scary. It can be chaotic. This equation, you change a little bit, and you're up with a completely different solution. You even don't know if this solution you get is the only solution you have. It depends always on the initial condition. It's really, there can be multiple attractors. So this has been very well studied, and this is the equation. But what has also been studied is if you drive these little nasty bubbles strong enough, you can actually create light and sound, shock waves. Yeah? So, and I'll show you just a movie of this bubble. This is a small bubble. It collapses. This is on the left side, you see the bubble, which expands slowly. So it's about 50 microns here in this size, and then it collapses. Yeah. And on the right-hand side, we see a shock wave. When the bubble collapses, it emits some sound, and this is a spherical wave which goes outwards. So it creates light. It's noisy, and that's why people have termed it a hooligan. Yeah, maybe you have seen, if you have not been at a football stadium, you might not know. They also do this same thing. They were rather noisy and this. So people looked at it and then plotted the radius as a function of time. Now you will see these are dots, individual dots. Don't try to do a derivative of these dots because you get all over the mess. Yeah? But you can put your model into it and then take a derivative of your model rather than doing it on your measurement data. So this is what you see. The bubble expands large, and then it collapses. But this we call collapse. Here, at that moment, when the bubble is collapsing and expanding again, it creates light. And there are extreme conditions created inside the bubble. Nobody actually knows what goes on inside the bubble. But this is interesting for physicists. That's why we work on this. So it's like a spring. Yeah? So it collapses, and there's gas inside, so it oscillates. And the jumps are lesser with time because you lose energy, because emission of sound and viscosity and stuff like this. Okay, so this one goes on. This collapse actually leads to energy concentration of order 10. So the energy density is 10 times higher to produce light than the acoustic energy in the whole flask. So you can just make the math. You are able to concentrate energy to this amount. So if you can concentrate energy to this amount, people have speculated, why not make fusion? I can assure you there have been reports that you can actually create a nuclear reaction with this bubble, but they have not been repeated. They have been published in Science, Nature, PRL, not been repeated. So it's still an open problem. So maybe a wrong measurement so far. But there is a chance that you can actually create extreme conditions that you can have nuclear reactions. I wouldn't bet on it, but this can happen. Whatever happens is if you have a bubble near a boundary, you create complicated flows, and you create actually a jet. Now let me go quickly through this. This is a thin flow through the bubble from the top to the bottom. See that here? This goes here from the top, go to the bottom, and then it deforms the bottom one. But this thin flows very fast. It can be up to 100 meters per second. So you have a bubble which shrinks, and not only it shrinks, but it creates also this fast jet downwards. And it creates always this jet in the direction where the boundary is. there is no boundary in this one, in this picture, because there is a boundary in this picture, but you don't see it. It's somewhere below each frame. A boundary is a rigid surface. The bubble actually moves towards the boundary, and it creates this fast jet. So this is interesting fluid mechanics, and it has found some application. Here. So there was an experiment done by the Australian Navy, and also this is in Singapore, rather interesting. I'm not sure it should be recorded here, but if you want to sink a ship, you can do it with a bubble. And this is done by a bubble. So what they do is they do an underwater explosion. They do it just below the bubble, the ship, and then the explosion creates a big, big bubble, maybe a meter in size. No, 10 meters in size. 10 meters in size, and then it shrinks again, and then you have all this energy concentration, and you get a jet which shoots upwards towards the ship hull. And it always shoots towards the ship hull, automatically. This is a very nice fluid mechanics. You will always get all the liquid flow focused onto the ship hull. And then if you do it at the right distance, you have sufficient impact to kill the ship hull, or break it apart in two pieces. And what you see here on the top is not the explosion, but is actually the jet shooting upwards. Yes. And I can tell you, the velocity of this jet is about 100 meters per second if you do it correctly. You dimension the torpedo, the charge, and the distance, 100 meters per second, and the water mass is about a meter in diameter. So you have about a meter in diameter water moving at 100 meters per second towards the ship hull. This is a real ship. It was an experiment done by the Australian Navy. There was nobody on the ship. No, I just put this bubble here. It's just to demonstrate that what is causing it, because the bubble now jets upwards towards the ship.
No, but the ship is not like 1 centimeter across, right? I mean, it's like 100 meters across huge ship.
The ship is probably 100 meters long or something like this, 80 meters, and the bubble maybe 10 meters. I don't really know what type of charge they use there. But this is, of course, security concerns, but it's also a way to maybe to sink some pirates, whatever. So you can do this a bit more harmless. This way I have done work on jetting, actually, by you can put shock waves onto these interfaces, which are curved, and then you can actually record the motion of these very fast jets in very high precision. And now what you see here, why we are expensive, is we are not only 1,000 frames, but we are taking 5 million frames per second. So that is fast. So that means about 200 nanoseconds between two frames. Yeah. So you get this type of, we were trying to use these jets to inject liquid into a skin. This can for drug delivery. That was some idea. So I'd show you how you actually record that fast. You build a camera yourself. And that was a big project. We started with a camera which was already built by the people who developed nuclear weapons. To measure nuclear explosions, you need actually sturdy equipment, but also fast equipment. And there was all the money available. So this development was done there. But they used a film. But now instead of using a film, we installed, at each spot where a picture was taken, we installed CCD cameras, 128 of these. And that's what here works. So what you take is you take a picture here, then you transfer this picture on a turbine here. You have some more imaging optics here. And then on each of these spots, you have a camera. And then while this turbine rotates very fast, there's a mirror on the turbine, projects the pictures on all these individual CCD cameras. So if you rotate the turbine very fast, you can record very high framing rates, if you do that sufficiently fast. So for the maximum recording frame is about 25 million frames per second of this camera. But to achieve this, you have to rotate the turbine at 20,000 rotations per second. So you can't do that actually in air. You have to flush the whole thing with helium. And you need a very special equipment, beryllium oxide. This was also very toxic, but you need special equipment or material to do that. And the whole thing is 2 meters high, and there's quite a lot of electronics behind it. But this is just a demonstration of how to record fast. It's not a trivial thing to record fast. So it does take some effort to make this delta T very small. So then when you do the jet analysis, you take the position of the jet at different times, and then you fit a line through it. Yeah? Initially you have a line, or maybe later on you have a line. And then you can do your analysis, and you can do your physics, and then you you plot, you love it. You make a plot of the velocity of the jet as a function of, for example, acoustic pressure amplitude. That's the incoming wave strength of it. So what you see here is we can get velocities of this jet. I showed you 160 meters per second, which is okay. That's good. But some time ago, actually not some time ago, very recently, in our lab here in Singapore, we made a bit faster jet. We thought actually, is there a maximum velocity this jet can get? The speed of sound. You know how fast speed of sound is in air? 330 meters per second. So we had 160 meters per second with this jet, and now we thought, okay, we can do it better. Actually, we can do it also cheaper. But here I show you a device. We do it a bit differently. Here we create actually a bubble just below an interface, and then you. Okay. Okay. Just look. We create here a bubble on the bottom, and when the bubble actually. Okay. Mm-hmm. So the bubble expands and then it collapses. So it creates actually two jets. When the bubble expands, it creates a jet, and when it collapses, it creates a jet. So a bit higher resolution with 500,000 frames per second recorded. You get one jet, and shortly afterwards, you get a second jet. The second one is much faster. And also the jet is not really straight anymore, but it fragments into small droplets. And then we measured the velocity, and we got 350 meters per second. However, this is a lower limit, because our delta t is limited by the camera. It can be faster. So the sound speed is actually not a barrier. So just for ending this short seminar, so for take-home message is that this is the limit. You have to do to measure, to find a derivative for a position with respect to time. That would be a velocity. Physical laws, that's where I come from, in many cases they are formulated as derivatives. There are laws which don't need to take derivatives, but most of our laws are derivatives. And one reason why it is because of Newton's laws, or set of laws, where we know that all the physical laws are identical in every inertial frame of reference. So if you want to find something interesting, or want something to find about the forces, we have to take actually 2 times the derivative, 2 times. Otherwise, we don't come to the force. That is the cause of an action. So this, I think, is at the heart. If you want to understand what the cause things, want to find a model, you have to take derivatives. Then, if you do experiments, you can't do the derivatives. There is no way to do it. However, you hope that you cover the right timescales. As I showed you, there's one, if the oscillation is too strong of it, and you would have a too low framing rate, you wouldn't be able to cover it. But this is also new science, actually can be found by taking faster movies. Another problem which I haven't addressed, but which is persistent everywhere, if you do a computer analysis, a simulation, you also have to take finite differences. And there, you are bound by the computing speed and also by memory. And both of them limit your delta t and your delta r. So in simulations also, you can't do this limit. And therefore, actually only in the beautiful world of math, you can take the derivative. Everywhere else, we have to rely on our limited resolution in space and time. But if you want to do good science, you make all delta r and delta t as small as possible. Now, I just want to acknowledge these are people which are working with me or have been working with me and provided all these movies. So I'm open. If you have some questions, I'm happy to answer them. Thank you. Yes. Oh, it can be a whole lecture by itself. We can use lasers, for example. You can shoot pulse lasers into liquids. That's the way you vaporize the liquid. You can use electrodes. You can also create a plasma in liquids, and then afterwards the plasma recombines, and you end up with a hot spot with a hot vapor, and this will drive a bubble out. You can use acoustics by high pressures. You have some small bubbles there, and if a high tension, you can rupture the liquid and create bubbles there too. And also by hydrodynamic pressures. If you reduce the pressure strongly, you can also bubbles. There are quite a number of ways to do it. Or the inkjet printer. You heat also the liquid up, and you create a vapor bubble. There we actually just introduce a gas bubble. We just the rose scallop. It's just a piece of metal of tubing, and then we put it under. Yeah. So there's always gas inside. So we just submerge it in water, and then you don't get it. You get a big bubble, and then if you submerge it in water under high pressure, then you get under low pressure, and then you release the pressure again. You get actually shrinkage of this bubble. That's why it's not covering the whole length. So it's just you entrap the gas by submerging it in water.
Why doesn't it get off the hole?
It doesn't?
Well, why is it moving slowly? Why is not the whole gas released instantly?
There is no gas release. Okay. There's no. This is oscillating.
Yeah. Why does it not?
So, but we drive we drive it with acoustic field. So what?
So there's some gas trapped inside, and how do you cause?
Yeah. So we took care that the gas is not covering the whole thing. Yes, by changing the pressure while filling. But then you drive the whole thing by an acoustic field. But acoustic field is just you have a sound. You heard this 1.5 kilohertz. You drive it rather strong, the sound, a few kilopascal, and then because if the pressure is high, the bubble will shrink. If the pressure is low, the bubble will expand. And you do it sinusoidally. That's why the bubble actually moves back and forth. It can't expand in the other direction. It can only expand at the back side. Yeah? So the gas can only expand to the left side. So if you look for the oscillation of this one, it's sinusoidal. The interface is pure sinusoidal. Yeah. Okay. Yeah. So we understand the fluid mechanics is a bit complicated, but if you try to blow out a candle, it's very easy. You just blow it out. Have you ever tried the inverse, sucking? No. But actually, you don't change the physics by it, but you have by outflow and by inflow, you have a different flow pattern. So you have a jet. The other one, you have flow from everywhere. It's a sink flow, comes from everywhere. So that's why the strength is not so strong. It's not so much of a velocity at the candle. So you can't suck it out. So you have. So that's the bubble. It pushes out a jet and it sucks in from all over the side. And both of the two have imparted different momentum. The two different flow types impart a different momentum onto it. And then actually the jet is like a jet engine. It's equal momentum forward as backwards. So net momentum is 0. Whereas the other one, this liquid from here and here, they balance each other, but they don't impart it directly onto the tube. So that's why it moves a little bit backwards, but not so much as it moves forward. Yes.
I think the measurements what you spoke here were always of the smaller scales. But I guess a similar problem would be for the large scale as well. Let's say for astronomical distances.
Oh, sure.
How exactly is it?
For astronomical, yes. Okay, there, to measure distances, you use typically spectroscopy.
No, I mean the velocity. Again, the problem of VRDD and the resolution.
Okay, so distances are in spectroscopy, in astronomy, they are, I think for close objects you can use triangulation, but further distances you use spectroscopy. And so you will end up with a uncertainty in your resolution, or in the in your spectrometer, on how much you can separate the wavelengths and how accurate or how much light you can actually gather from these objects.
Subject to the scenario where you can use such a thing.
Yeah, so always with measurements, you will end up, you have to find a scale to it. And let's say for the high-speed camera, the scale would be the movement between two frames. So that is your limiting resolving power. If you want to do look for sizes or distances on a CCD camera with a astronomical equipment, you will have a limited number of pixels. And if the object covers only 1 pixel, then you will only see a difference between if it has moved from 1 pixel to the next pixel. So there are the resolving power would be given by the coarseness of your photographic equipment.
So could I say bubble here as DR because they say with this question?
Oh, right. Yes. So there for the distance, yes. But for distance, you have always the DR. Astronomical, they have no problems with it with DT because the times are are long.
In the acoustic windmill, how were the bubbles made to oscillate?
The same way. The same way. Each. Oh, sorry. Now, each of these, in each of these, one is a bubble inside. And then they are oriented such a way that each makes a forward. So each of these makes a jet. It moves in this direction. That's where you get a rotational motion. Okay, it's a bit nasty. You have to fill.
But the bubble itself is driven through some field?
Yeah, through the same sound field, yes. So here in this, maybe you can see. So what we do is we look actually from below. We look from below, and I think the sound field is here. On this side is the piezo. But because the wavelength of the sound is larger than the container size, so a few centimeters for this frequency, and the container size is 5 centimeters, and the wavelength is about something like 20 centimeters. Each of these bubbles sees about the same pressure. The wavelength tells you how much the pressure varies over space. And the frequency is by 1 kilohertz. It's so large that every bubble sees about the same oscillating pressure. It's a loudspeaker. It's a loudspeaker, and there's a special loudspeaker. We use a piezo crystal. It's a crystal, and actually it's a ceramic, and it's polarized. And there's a piezoelectric effect. If you change the voltage on the surfaces of it, it can contract or expand. So it's or other way around. If you press it, you create actually a voltage on it, a potential on it. So it's a piezoelectric element. You have it actually in many of the handphones and alarm clocks or pocket calculators. Whenever they create some sound, they have a small ceramic which is then driven by some electrical signal. Yes?
The experiment you often see in the show, where did they release bubble from? From shoreline or?
Okay. This is militarily classified, but because it's physics, I happily share that with you. And I have never worked for military, so whatever I share is. So what you want to do is you make a bubble below the ship hull. So you shoot a torpedo, actually, and you make the torpedo explode once it is below the ship. Yeah? Then you create a big bubble, and the bubble doesn't move further with the torpedo because it expands so quickly, and the drag is so large, it will just fill the space under the torpedo, under the ship. When it actually expands, it bends a bit the ship because the expansion force, but it's not causing too much of a damage. When the bubble collapses, it creates this jet towards the ship hull. And there's this optimum distance, let's say distance versus size of the bubble, where you get the strongest impact. It's about, for 10-meter bubbles, you put it about 20 meters away, or actually 24 meters away, from my experience. So if you want to have a torpedo, you shoot it 24 meters under the ship hull and make a 10-meter bubble. But this is just basic fluid mechanics. You find it in open literature, how to get the maximum effect on the ship hull. They don't care about that. This is military science. They developed this since the Second World War. The Germans were very good in building submarines and sinking ships, and then these were taken over by the Americans and the Russians. And actually, there was a big accident. This Kursk, I've heard about Kursk. That was because they tried another type of torpedo, which was a bit more nasty. They covered the torpedo in a gas bubble, so it doesn't really see the liquid. And they can go up to 1,000 meters per second. 1,000 meters per second, this torpedo. But you need a lot of explosive charge, and there was a problem with this.
So you mean to say that the Americans stole the German technology?
No, they didn't steal it, but they invited the scientists. But this is history. No, I think this is the initial problems with new weapons. Yeah, you have to master them, and that is one of the problems.
The torpedo under the ship, did they do this because that is an alternative to actually striking a ship?
No, what they found out probably that just by applying these weapons, that it's more effective to explode the torpedo below the ship than just ramming it into the ship.
So it is more energy.
I wouldn't call it energy, because the energy is anyhow gone once you have to shoot the torpedo. But you want to make a maximum strike on your enemy. This is it's a fluid mechanic problem. It's an interesting fluid mechanic problem. But you can scale it down, you can scale it up. So in small scale, you can use it for beneficial use, for drug delivery through skin. You can use it for cleaning your teeth. Something like that happens too. You have when you do this cleaning of your teeth with this ultrasonic probe at the dentist. They use something very similar. Bubbles are also created there. And they clean it.
The jet created by the bubble, is it more, has it had more energy than the bubble itself?
No. It actually never really matters on the energy. It's like the sun is coming onto the earth. There's lots of energy, but mainly we get a sunburn. But if you focus it, you can get a fire. So the concentration of energy is important for a lot of things. So if you concentrate all the energy of the liquid, the kinetic energy, into the tiny spot or into this jet, yeah, you transform this energy onto a small spot, then you can get a big impact. Yeah?
Thank you very much, Prof.
Okay.